query execution models is about how data flows through a database system and what options you have to organize those flows. And like back in the 80s and 90s, this wasn't so important, even though it had some importance, you will see in a moment. But it's getting more and more important as modern database systems run in main memory most of the time. And most of the data fits into main memory. And there you have to really be careful how many function calls to execute and how to move data around in your storage hierarchy. It plays a much bigger role how to execute these things, and you will see. And that's what this lecture will be about. So here's an alternative view on what you have in a database system. So you have some declarative query here. Oops, some declarative query here on top that goes through the query parser, then through the query optimizer. And the query optimizer's job is to compute a plan for such query. And this plan is some sort of physical execution plan consisting of these physical operators. So we have the simple hash join. That we talked about these different algorithms last time, how to execute a join. Here in this plan, you see there's a simple hash join on top. There is a merge join here. There's a sort operation. So I'm splitting up the sort operation from the actual merge join. This merge join here is just performing the merge, assuming that both inputs are sorted. That's one way of representing that. Sometimes you only see one entry for the merge join, and that includes the sort operations. Here I'm not doing that. Here you already see that there's a sort on the left. Make it big a little bit. Sort on the left and a filter on the right without a sort. So that's a situation we also talked about last time. It could be that one of the inputs or both of the inputs are already sorted on the join attribute. So you don't have to do an additional sort. It would be stupid to do that. So we see it here as we have an ISIM axis. So that sounds like a B tree where the entries are already sorted with regards to the join tree, to the join predicate. So you don't have to do an extra sort. This kind of property where you do not have to, where you can exploit an existing order on existing property of the input stream is also called an interesting order. Oops. Interesting order. And that happens here. Yeah, the B tree already gives you the sortedness property you need for the merge join here, thus you don't have to sort again anymore. Okay, so the entire thing here is called the physical execution plan, or physical plan for short. And now we are in the situation, okay, nice, we have these physical operators on the slide. How do we execute this stuff? And there are two main classes of techniques you can use here. And one is you basically call precompiled modules, functions, iterators, and whatnot to execute the plan. That's something we did in the undergrad lecture. There we had this relational algebra library in Python, and that's basically doing what we see on the left. This is called plan interpretation. Basically, we initialize a couple of operators, of elements of the plan, glue them together, and then execute this plan. The other class of methods is called code generation. So in code generation, you do something similar to what a standard general purpose compiler does. And that is, you take the description of the plan, which is this is the description of the plan, and then you generate executable code for that. It can be done, can be done in many different ways. One is to create LLVM, use LLVM for that. We have a prototype in our group where we use WebAssembly to create code. You could also create C++ code. However, you have to be careful. If you create C++ code from this one, you will pay a higher price for passing the C++ program. So I would take the physical execution plan. So here's my plan. Whatever, that's also called the query execution plan. Physical execution plan is all the same thing. And then I translate that into some executable. Let's call it executable. But how do I do that? Typically by generating some intermediate language. Could be C++, C++, WebAssembly, bitcode, and LLVM, whatnot. And the problem with C++ or with any representation that's textual could be that, okay, if you create a text file in C++, then you have to parse it again. That may incur, trigger some additional costs for parsing. So keep in mind that the query comes in and the user expects the database system to return query results. So the end-to-end time, end-to-end, from the user, here's the user, talking to the DBMS, that sends a SQL query and wants to have results. So we're here where we're now discussing whether, so the query optimizer did its job, it's translated the SQL into a query execution plan, and now we're discussing whether we are compiling that into a program, and then execute the program to return the results. So whatever we do here in this space will add up to the overall perceived execution time from the user. So the user will feel the price if the compilation time is too high. And that could be a problem that have to factor in. So whatever we do now in Magic in the following slides in terms of translating the query execution plan to some executable, or to making a decision how to, based on this plan, compute the results to the plan, that will add to this overall end-to-end time perceived by the user. And what is a good technique to lower those costs? Query comes in, database system does magic, optimization, compilation, execution, returns the results. That's the overall end-to-end time. What can I do here to lower that time in general? And that's the first thing you do, Sometimes, okay, how do I start? So the idea is really of SQL is declarative, and the optimizer optimizes it. And there are situations where even though you have two SQL statements that specify the same thing, the optimizer does different things. That's the problem of the optimizer. It shouldn't happen, but it happens. That's true. A good example is semi-joins, when we talked about this result DB stuff. Semi-joins can be declared in different ways in SQL. But that shouldn't happen. So for complex queries, you still run the optimizer, and you want to do that. Otherwise, query execution time might be terrible. There's the other very easy technique most database systems offer. And that's the first thing you should look at. No one remembers. I think we briefly touched upon that in the undergrad lecture when talking about SQL injection, because that also fixes the SQL injection problem. Prepared statements. Prepared statements. That's a technique provided by many database systems, and that allows you to send a SQL template, so to say, where you keep some of the parameters open. So rather than saying in your query, whatever, there's a where clause, where a equals 42, you can send a query like where a equals, and then some parameter. Then you submit the query, you prepare the query in the database system. The database system will run the query through its optimizer, provide code for that, ideally, depending on the implementation of the database system. And then you can call the query like a function. You can call it like a function providing that parameter, and the database system will execute that pre-optimized, that pre-compiled plan. So all the time for query optimization and code generation is only paid once when you prepare that statement. Then once you execute the statement, you don't have to do that anymore. Yeah? So you just execute the precompiled program. Yeah? Same as with the general purpose compilers. And general purpose compilers, you open a program, whatever, some image editor. At that point in time, the program was already compiled. Everything else is parameters. You don't compile the program when opening it. So that's an important technique you should look at if you have performance issues with that. Right. And then there are many other techniques, but that leads too far. Okay. So here is another visualization of what I just explained. So on the right is this plan, and now the question is what to do with that. So one interpretation is, yeah, this is kind of function calls. And I think our Python library in the undergrad lecture does something like that. So basically, each of these operators can be interpreted as a function. And here's the expression as a function. So basically, where's the innermost function call is this. So C is your input relation. You call a function scan on C, and then this scan operation returns all the tuples available in C. Yeah, returns it as the input to the next operation, to the next function, which is the sort function, which takes all these tuples produced by the scan, sorts it, and again outputs the sorted stream of tuples, which is then again used as one of the inputs for the merge join. The merge join has two inputs. What I just showed you, this part, and there's a second part, which is a filter, which is the second parameter to the merge join operation. So it's just a big function tree. That's one way of seeing that word. Right. But the problem with that is intermediate results. So in these query plans, it may be that certain operations produce very large outputs. And these outputs are called intermediate results. So everything that's produced here is an intermediate result, that's an intermediate result, and so forth and so forth. This on top is the final result. Yeah? But all the edges you see connecting these operations are intermediate results. And if you do that naively, like here, and the inputs are large, then you pass around tons and tons of data between those operators. You don't want to do that. That's a lot of information to pass around. So the question is, can we lower the memory pressure for these kind of executions? Yeah, and one approach is called pipelining. And the analogy I will be using is, it's really like a little bit like water pipes. How does data flow from a source to a sink? The source here being here and the sink being there. So you always see these two elements in these plans that, or in these pipelines, that data is generated, like here from this water tap is the name, and then it flows through a pipe into a sink, and then here at this point, another pipeline, another water flow might be generated. And that's how we will think about these plans. And just that we don't, the idea is to have data flowing between those operators, between these operations. Yeah, so we have sources and sinks, and another name for that is producer and consumer. I mean, if you ever used Unix terminal pipelines, it's another example for pipelining, of course. Here is a related concept. However, you will see there are many ways of implementing these different concepts. Question? Question? No? Okay. So we are producing data / water, and we are consuming data / water. Yeah. Why do I show that twice? That's doubled. I don't know why. Okay. So here is a fully connected plan, so to say, where I pipeline the data through such a plan. Again, from the structure, it's the same thing I just depicted on a slide before. So the data is flowing through that pipe system, but there are certain operations attached. So here's a sort operation, here's a filter, here's our merge join, and here's our simple hash join. And now we have to look at, okay, does it even work that we can simply pipe data through such a pipe system? Or what are the issues here? And One thing is these so-called pipeline breakers. So if you think about the operations that are available in such a plan, there are operations that require to consume all data before they can produce a result. A good example is a sort operation. If you want to sort an input data stream, there's no way you output the first result tuple before you haven't seen the entire input. No way, because in the input there could still be another tuple that's the smallest element to produce. So what happens in the sort operation is it first has to digest, first has to consume all of the input here. Basically, it buffers the input somewhere in kind of a water tank, fills up the water tank with all of the input that comes from this scan operation. Only once this input is exhausted, so only at that point in time when all input from C was seen by the sort operation, then you can make a decision. Then you can say, okay, I've seen all of it. Here's the smallest tuple, second smallest, third tuples, and so forth and so forth. And that's called a pipeline breaker because, yeah, I mean, sort has to see everything. In contrast, a filter operation, this is a per tuple operation. Yeah, filter is defined as you evaluate a predicate on a specific tuple. A equals 42 or here A3 equals 12, and this example is a predicate. So this can be done tuple by tuple, water molecule by water molecule. You can make a decision, yeah, this holds or doesn't hold. If it holds, you pass it on in the pipe. If it doesn't hold, then you have to remove it from the pipe. Yeah? So you don't have to consume the entire input to make that decision. So this is a very, very good, this operation behaves well in the pipe system. The sort operation doesn't behave so well. Merge join behaves also super well because if, as I defined it here, the sort is a separate operation, so the merging is just this walking through these two sorted input streams simultaneously, as we talked about that last time. This behaves super well in the pipeline. You don't have to buffer much data. It's really just a pointer to the next and stuff. Yeah? It's really behaves super well in the pipeline. Then simple hash join, as I explained it last time, simple hash join, what does it do? It creates a hash table on the left input. Once that is done, once the entire left input was consumed, so everything from here has to be put into the hash table. The water tank is a hash table. Yeah, so it consumes the entire left input. That means simple hash join is a pipeline breaker with regards to the left input. Everything is copied into the hash table. Once the left input is exhausted, so that's the build phase, then the probe phase starts, and probe phase means everything that comes along this pipeline is probed against the hash table. But there, again, there's no pipeline breaking here because you have one tuple that comes here, you probe it against the hash table, produces some results, you pass it on to the result. So the probe phase of simple hash join behaves well in the pipeline. Yeah? So there's no issue with regards to that. So you see there's a mix of operations all of a sudden that behave well in the pipeline and others do not behave that well. And here's another visualization of that. Yeah, this is simple hash join, or index nested loop join is a more generic term for that. This is reading or bulk loading, aka the build phase of that. I can write it down again. Build phase. Yeah. So, so you build up, you fill the water tank, the hash table, that's our hash table. Then at some point the left input is exhausted. Okay, now you close this valve. Now here only this was open, this valve, this was closed. Yeah? Now you close it again. And now comes the third phase, looping and probing. This one also called the probe phase in literature. And here you see, aha, this is closed, this is open, and this is open as well. But the flow is really, here's a data tuple, you probe it against the hash table, and if it finds a match, you produce results and send those results directly up to the next operation. So probe phase, everything is good. Build phase, that can hurt. So in particular, and we talked about that last time, then maybe, okay, so what happens if none of the inputs fits into main memory, yeah, for a simple hash join? I told you, okay, simple hash join is a good idea, at least if one of the inputs fits into main memory. But if both input tables are too large for main memory, simple hash join doesn't work, and then we go into co-partitioning the data. But as long as one of the inputs fit, yeah, and that's exactly this situation here, yeah, if you can build this hash table in main memory, everything is fine. So another extreme approach, and people also did that, is that, okay, so if this doesn't fit into main memory, you can't initialize a hash table, but that doesn't imply that you cannot run the index nested loop join, because you could do what? Now the problem is not the join. The problem is a hash table if there's not enough main memory. So what could you do instead? The join operation is not killing your memory. The hash table is killing your memory. If you can't fit your hash table into main memory, it doesn't mean you cannot initialize this index nested loop join. So you could use an index that resides on external memory, like a B tree, in theory. It works, yeah? Something that doesn't eat up so much memory, that in an external memory structure like a B tree or anything else, where you don't have this hard condition that everything has to fit into main memory. Yeah? For B tree, it doesn't matter. You can put it on disk and can be arbitrarily large. Of course, then you have different performance metrics. Yeah? So typically, this is not done. But in theory, you could do that. So bike load a B tree on the left input and then probe everything from the right input against the B tree. Here's your join. Yeah? Okay. Quick sorting is another visualization which is very similar. So you read the data, break the pipeline. Yeah? Here, everything, pipeline is broken or shut down if you want. Then you sort it, and then you output it. Okay? Just as a footnote, so how do you compute the k smallest element of a data set? Or the smallest element of a data set? So it's a variant of that. Basically, you have sort operation, sort, but then you have a top k. That's like the top three elements. You're only interested in the minimum three smallest elements. Yeah, you can sort the entire data set and with quick sort, and then you return the three smallest elements. It's a good idea, bad idea. Call your quick sorting function inside this operator. Quick sort, for instance. Quick sort. Yeah, quick sort it, and then only return the first three elements. Is that a good algorithm or a bad algorithm? Yeah. Yes. And if it's lower than the yes. One, you keep it on the right. Exactly. Yeah, that's actually a good algorithm. Yeah. So what he's saying is, rather than doing this stuff here, you could basically need a list of the smallest three elements seen so far. Now you consume the entire input. Yeah. Whatever our input is here, I don't know, R. Yeah, and for each tuple, you see whether that is smaller than the stuff you've seen here. If that is the case, you replace that. You can also support that by a priority queue, in particular if k grows bigger. But that's the best algorithm you can do. That's much faster than sorting it. Even for quicksort, you could make the case, okay, if quicksort does something like, okay, this recursive partitioning once you did this partitioning step, the idea of quicksort is, yeah, you call quicksort here and call quicksort here and so forth. It's recursion. You don't have to call this one at no point in time if this is still greater equal 3 elements. Yeah? And so forth in the recursion. Yeah? As long as you can basically go left deep in the recursion tree, and only on these 3 elements, everything is fine. Because this sort step, once you partition the data into these 2, you know that everything to the left of this pivot element is smaller equal. So you never have to call anything here anymore. Yeah? So you could adjust quicksort to be a bit cheaper, but what you suggested is actually the algorithm. Why am I explaining? I think that's because I'm explaining this again because some guy on YouTube recently explained that you to compute top K, I got really mad about that and wrote a comment. I already write comments on YouTube, but so he explained that, we want to compute top K, so we do an external merge sort. Yeah? Did a full-blown external merge sort and then selected the top 3 elements. Please don't do this. Don't do this. So you can really do much more efficient things here. Okay. And many aggregation operations go in that space. Minimum, maximum, count operations, stuff like that. That's all in that space. Okay. Here's a similar visualization for external merge sort. So run generation goes here. Then merging without the final merge still blocks. Yeah? All these intermediate merge levels. We still cannot produce any output result. But once we initialize the final merge, and I don't mean we pulled all the elements from the final merge, but once we initialized it, everything else is now is not blocking anymore. It's just this initial run generation and the intermediate merges that block the pipeline. Yeah? So all the algorithms we ever talked about in query processing can now be mapped to their behavior in the pipeline. Yeah, and that's basically the algebra, so to say, or the operations, the physical operations you have. So blocking, this index nested loop join, simple hash join is blocking. Bulk loading an index is blocking, yeah, because if you have to consume the entire input, sorting is blocking. And then there are these non-blocking algorithms. That is the right part of the index nested loop join. Or this situation we also talked about that the index is already there. Yeah? We talked, when I introduced index nested loop join, I said, okay, it could happen that there's already an index available in the database system. Yeah? You ask the catalog, it says, yeah, I already have the index. Why do you want to build an index or a hash table? I don't care. Yeah? So then you're already non-blocking. Filters are not blocking, same for projection, merge operations, merge joins, non-blocking. And this is another, let's ignore that algorithm. So there are actually algorithms that are fully non-blocking. And this is called double pipeline hash join, but you don't see that these days so often anymore. Okay, so here's an alternative representation for the same plan with all these water tanks here. And now let's talk about how do we implement that. So how do we implement the pipelines? This visualization with water is nice, but what the heck, what are the interfaces for that anyway, if I do it like that? And there are many, many abstractions in databases. Typically what we say is database researchers is operators, yeah? but you should know iterators. Yeah? Have you seen iterator? It's in any programming language. Or generators in Python. I think I used it also in the first months of this lecture. I think the get function of our indexing interface is a generator, for instance. So you can use it in a loop directly, yeah? And it has this effect that elements are produced on demand. Yeah? Result set is another similar interface that's used by JDBC. So JDBC is a driver that you can use to connect your Java program to a database system, and other connectors, database connectors have very similar interfaces. Okay, So this is a classical interface that you need. Yeah? And the idea is really that any operation you saw in relational algebra can now be mapped to such an operator. So an operator only has these three methods. One is open. This is kind of similar to what you would be calling a constructor, but sometimes this is not done in the constructor, but really a different method. Again, depends on the library you're using. There's a close operation. Feels like a destructor. Again, doesn't really work in Python. C++ works much better. Yeah, so in Python, you have finalizers, not really constructors. Long story short. Yeah, so this is a method to initialize stuff, the open method. And this is the close method is something to destroy stuff, yeah, free resources and stuff like that. The only interesting thing is this one. That's the next method. Next is called by a user, and next returns the next piece of data, which here is denoted as a chunk. Yeah? The next chunk of data or signal could be a null pointer that no more element is available, or could be an error message. Yeah, here's an example using Java. Yeah? So that's iterator from Java. So I think that was available in Java already in the 90s, this interface. Yeah, so that's the same idea, just slightly different spirit. Here you have an extra method, hasNext, yeah, that can be called to ask whether a new element is available. Then there's the actual next method. Then there's no close method. There's no open method. It's all done via the constructors and destructors. And there's an additional remove method. Yeah, that's one other realization of such an interface. Yeah, and then you could translate our plan to something like that on the right. So now all of these become classes that implement that operator interface. And then we can think about how the flow in such an operator tree actually happens. And that's important to understand. Now, once you initialize this operator tree, now the user has a handle to this tree. Yeah? So the user basically yeah, you have a query execution plan. Query execution plan. And in your program, the user now calls open. Yeah, that's the contract the user has to fulfill in the programming language. It says open the plan. And the plan consists of these operators, the top level operator being this simple hash join. Now, that's the top level operator. And this has two child operators. Yeah? One is this iSeek, the other is this merge join. The merge join again has two child operators, sort and filter. And the sort only has one child, the filter only has one child. Now by calling open, you trigger a cascade of operations through the tree. Yeah, so the open on the root operator here, yeah, that's what's visualized here, triggers, delegates the open further down the tree. Yeah, so this operator, the simple hash join operator, will also call open here on the iSeek, on the merge join, which in turn call open on all the other operators, yeah, to make sure that the tree is ready to produce results. Yeah. Then, once that was done, so the tree is ready to compute stuff, now the user can call next. Yeah. So once this call returns, you could say, okay, whatever, my next tuple or next chunk or whatnot is determined by calling QEP, query execution plan next. You call the next method. Yeah? And that method then should do all the necessary computation that's required to produce a new result, to produce the next result, sorry, but not more. So open does not imply that the entire query result of this plan is produced. That's very important. We want to be lazy. We want to do a lazy computation. Only initialize the query execution plan. And then here, the contract of next is just do the computations necessary to be able to produce the next result. But you don't have to do the computations necessary to compute the second result and the third and so forth, just the next. So just anything that's necessary to satisfy that demand here. Yeah? So when the user calls next, this next will already be propagated down the tree. Yeah? And what you see here is even in the open call, it may happen that next calls are issued. Yeah? It depends again on the implementation. But here, if here's a good example. So you could, it can be implemented in different ways. Yeah? But that's one way of implementing is shown here, that when calling open here, the open will be delegated down here, but then already as part of the open phase, you execute the build phase for the simple hash join. And how do you do that? Well, you have to get all the elements from this operation. How do you do that? You call next. Yeah? And you call next on this operator as many times as you have tuples, as you have objects that are returned here. As you call next for each and every tuple, insert it into the hash table, and then you could actually already call close on that input. That could be done like that in the open phase. Yeah? So the operator, the tree is already ready, is ready for producing results. And the same happens here. Yeah? Here you see it. There's a sort operation, and you could implement the open method of sort to already consume the entire input, put it here, sort it, and then be ready for the first actual next call that's coming down here. Yeah, you see there's only an open call, there's no next call, but open could be implemented to be ready to immediately deliver the first result from next. Yeah? That's what you see here in this visualization. So there are tons of calls that go down, up and down the tree actually, just by calling open here. Okay. And here I assume one chunk is one tuple. That's a standard way of implementing it, and that's how it was implemented in the 90s. Yeah, the 90s was really tuples, tuple. Yeah, then actually there were a couple of papers that said, why not batch of tuples? Yeah, batch of tuples. So you would say, okay, why does the next call only have to return a single tuple? Yeah? Because if I have so many calls, maybe I want to reduce the number of calls. Why not every time return like whatever 10 tuples? Yeah, that's another variant of that. That's what was called batching. Then column stores came along. And then all of a sudden, this was called vectorization, which is a completely stupid name. But when you now hear people talking about, oh, we have a vectorized database, what they actually mean is that, they pass around batches of tuples in such a tree. That's just a fancy new name, which doesn't make too much sense, just as a footnote. Okay. Right, yeah, this is a visualization of when you actually call next. Yeah, so we're here, yeah, and that is what happens here. So the user calls next. Okay, we don't have to go down here because we already executed the build phase before. Okay, but you have to get the first element here, so you have to pass down the next here. And then the merge join has to make sure, okay, how many elements do I have to draw to find a join result? That depends on the join selectivity, of course. Yeah, so it's not clear how many elements you have to draw from the left and from the right to be able to produce a first join result. But here again, the pipelining helps because the merge join only has to do that amount of work until it finds the first result here. Once that was found, you can probe that result directly against the hash table. If there's no result, okay, you have to go back and again trigger the merge join to produce more results until eventually you produce a join result here and return it to the user. So it's really demand driven. It's really lazy. The entire plan execution is super lazy. And this kind of execution has many, many advantages. One is, yeah, you're lazy. You only do the stuff you need to compute. And once you implement your operators like that, in that fashion, you can basically plug all these operators into one another and everything happens automatically. That's fantastic, yeah, in such an iterator library. Yeah, and the other is also that note that if you do something like that, there is not this problem we had before when we implemented this with function calls. If you implement the merge join as a function call to return the entire result set of the merge join, you have many problems. One being it's blocking. Now all of a sudden you have to wait till the merge join returns all of the tuples. And it's a lot of data being passed around. What I'm passing around here is only the stuff being returned by the next call. Here it's a tuple. Yeah? If it's a batch of tuple or vector, yeah, this is still a relatively small part I'm passing around in memory. So I'm not wasting resources by passing around entire result sets. Yeah? So it's a very good way to organize such a pipeline. Okay. Yeah, just for completeness, this is how it's done in the result set interface. Yeah, and then basically, that's what I already alluded to. This is a parameter, yeah, whether you pass around. Yeah, this is basically specifies what you operate on. Is it rows? Is it columns? Yeah, iterators can be used to iterate on pages. You can implement the next with a page, with a chunk, whatnot. Yeah, many options here. Idea is always the same. Just produce the next chunk of data, and then allow consumers to do computations on that. Yeah. Okay, here a couple of examples with the simple interface. So open, next, close. That's also the reason why this is open, next, close. So this is sometimes called an ONC interface. It's a very old name for that. So these days people say operator or iterator interface. Cursor is another interface for that. So that, I don't know, 24 names for that. Here's projection operator, huh? How this could be implemented. So what you need is an input operator, that's a child operator, and you need a projection function. Yeah, you see it here. And then you have the open method, which delegates the open down to the child operator. Same happens here for the close, delegates it to the child operator. And here you call next. Yeah, so you consume the next, here you call next on the input, on the child. And in this implementation, you assume that if null is returned from the child, the input, the child operator is exhausted. Then you stop. Then you return null as well. And that's a signal to the operator on top that it is exhausted. That's one way of doing it. But if it's not equal null, you basically return the projected tuple. Yeah, so f is the projection function projecting the input row to something. That's all you have to do. In Python, you would actually implement that through yield. Have you seen yield somewhere? Yeah, you can also search it in our Python database system. It's used in many different places. It's fantastic and it's super helpful. Here's a selection operator, very similar. So you consume the next, you run this next in a loop, and then if the selection says, yeah, that's okay, the next temporary row I'm getting from the input here actually qualifies under my selection predicate, then you return that. That's how you implement selection operator. The problem with loops then is, however, something like that. So this is an enumeration operator. Yeah? If you implemented that in Java or Python naively like that, that wouldn't work, of course, because here, every time you call next, you would reinitialize this start condition of the loop. Yeah? The first time you call next, you say, yeah, and if the enumeration is supposed to enumerate a certain range, yeah, like this interval from 42 to 55 or something like that, every time you call next, you would initialize the loop with this from variable. Yeah, so you would always receive the same number. Therefore, an important workaround here is to keep the internal state of loops as state of the entire object. Yeah? So you basically move the current field as a private state attribute of the operator. That's one way of doing that. The other is in Python again simply called yield. Yeah, then you can do for e in range tralalalala yield what? Yield e, and that's it. That's super neat to do in Python. I'm not sure whether Java now has a yield function. Does anyone know? Yeah, they have it? No, okay. Huh?
I think so, yes.
Ah, yeah, okay, cool. Because when I did those slides, I didn't. It's been a while. So I didn't have it yet. Yeah, so this is a pull-based interface. So the user pulls from the plan. But another way to organize the data, and again, maybe that's a discussion we just had if you don't understand German. So you have to differentiate the data flow and the control flow. The data flow in the pull-based query plan or this tree, this operator tree, data can only flow from bottom to top. Yeah? Assume the gravitational force is on top. That's the data always sits in the leaves. They're like in relational algebra, same thing. That's a convention that exists there. If you inverted the plan, it would become, maybe I should invert it for the next iteration of the lecture. But basically, the data only flows up, no matter what happens. Yeah? So assume there's a black hole sitting here, pulling all the data, attracting all the data. In contrast, the control flow goes top down. So the user calls on the top level operator, and then additional calls are triggered, and a cascade of calls is sent through the operator tree. Yeah? So calls go down, data goes up. Yeah. That's a confusion here. Okay, and that's a pull-based organization. And now let's look at the inverse, and that is push-based organization. And that was, I think, the first time I came across it was a long time ago. It sounds like a trivial software engineering thing, but it has quite some implications and interesting use cases. So the only thing that's being changed here is, so far we talked about pull operators. You call next, and then you return a chunk. Now it's the other way around. You call next, it doesn't return anything, and you pass the next chunk of data to be processed. And when you put them side by side, it's something like this. So in the pull universe, you have this top-level operator that's sending a function call down to the child operator, telling the child operator O1, hey, give me the next element. Yeah? So O2 calls next on O1's pull API, and then O1 returns the next element to O2. So the control flow is triggered by O2 down to O1, yeah, which is then instructed to return the next data element, which is flowing up again. Data flow goes from bottom to top. In the push universe, it's the other way around. Here, O1 calls next on O2's push API and passes the next element to O2. So here, both the control flow and the data flow show in the same direction. They're both bottom up. Yeah? And the interesting thing with this is that this triggered an entire class of systems called data streaming systems. So data streaming systems. There are many, this happened around 20, 25 years ago. Prominent examples in that space were Telegraph CQ is one name of a system, and Aurora Borealis. Those were Borealis. And a couple of spin-offs were created also from Marburg University, where I graduated. There was XXL was a library that did that in Java, also with push-based interfaces, very similar ideas. And the idea is, if you have sensors like that measure the temperature, for instance, in a room, assume there was a sensor here doing that, so here's your sensor, yeah, then that would send it actively. Every time it measures, it would send that data item to some other processing step. Yeah? Assume there was an entire pipeline. Assume, I don't know, an aggregation operation. Yeah, a couple of sensors. Yeah, there's some sort of aggregation operation here. So rather than the aggregation operation pulling the data from the sensors, this would invert the control flow in the sense that once something was produced, it was immediately sent from the sensor upwards. So that would invert the control flow. And if you do something like that, you have a much better match to these data streaming systems that do exactly that. So the pull-based organization doesn't really work there. And that triggered a whole universe of systems. And we will also see, I hope we get there today, is that modern database systems that compile their plans. Remember what I said initially today. You can either interpret the plans, that's what pull-based interfaces are doing, or you can compile it to an executable program. In these executable programs, most database systems I'm aware of, they actually use a push data flow rather than pull. Yeah, so pull is something that's often used in connection with interpretation, whereas push is used with compiling a plan. Okay, so here's also something we discussed a bit in the break. So here's again both universes, pull on the left and push on the right. And you will see there are operators that are both sources and sinks. Yeah? So here this operator O1 just produces data, but it doesn't consume anything. In other words, there's no child operator for this operator O1. That's why there's only this image of the source. Yeah? Then this operator O2 is both at the same time. It is a sink and a source. It is a sink with respect to the data coming from O1, and it's a source with respect to the data being sent to operator O3. Yeah, so you have operators that serve as both, as source and sink, and then you have operators that are only sources, and you have operators that are only sinks. These three cases are available here. Yeah, and then you can reason about how to organize the data flow. I'm not sure whether we have to show all detail here, because we already had it on the board. So here, it's triggered by O3 in the pull universe. In the push universe, it's triggered by the leaves. The operator O2 here pushes the data computation through all the operators on top. I think I shortcutted here a little bit. Yeah, that's okay. Yeah, then you can think about the different interfaces that exist. I don't think we need that detail here. But that is important. Yeah, I think this is something also to kickstart compilation. And now, in the next minutes, I will show how to compile such a plan. And when you think about that, if you compile that in this push-based universe, you can split a plan into so-called plan segments. So the idea is you run loops for certain segments. For instance, here, this is one loop. Yeah, if you want to translate that not into operators but into code, you run a loop that does all the stuff you see here, including building the simple hash joins hash table. Yeah? That is one of the loops you run. There's another loop that just scans C and sorts all the elements of C. Then there's a second loop that's being run here till the merge join operation. And then there's another loop you could run here across that merge join operation. Yeah, that's one way of organizing this pipeline. But let's make it more concrete, and let's look at the notebook we have here. So it's a code generation notebook. Here we go. And assume you want to execute a query like this. So select star from persons, join books. So just on name equals author, so just a join of two relations with a simple condition, oopsie, on books. Price should be strictly lower than 10. So we create some fake data here, a list of person instances, a list of book instances. Again, we use this faker library we used before many times. Set the C to make it consistent, the results. And if you do that, you see that's what we get. So we just show the first 10 elements of persons and books. Yeah. Persons have a name and a birthday, books have a title, and an author and a price. I think we used that before in another notebook. So now we write that data to files, persons.pickle file and books.pickle file, and we create a query execution plan. So this is an operators library we implemented in our system that does the same thing as I just showed. But what you can do here is you get a textual explanation of what this plan is doing. This is very similar to what you get in a database system. Not sure whether you ever did that. You can send a SQL command, but most of the systems also allow you to write explain, plan, select, tra-la-la-la-la, yeah? Or explain, analyze, or explain or something like that. Yeah? So rather than getting the query result, you can ask the database system, hey, give me your physical execution plan. That's what you're seeing here. Yeah? So an explanation of how to compute the stuff. And you see, the idea here is I'll do a simple hash join. That is my join condition. And then the nesting is the child operators. So you have a scan on the left, and you have a filter operation on the right. Yeah, so those are the two child operators of the simple hash join. And the filter operation, again, has one child operator, of course, that is a scan on this books data set. Yeah, and now we have these two ways to compute results to the plan. One is this interpretation, and in our code we are calling it interpret open. Yeah, and that computes this result. Interpret open also spills out all the data, so we also include producing all the tuples. Yeah, it's not split in a separate next, it's push-based word. Or the other option is to compile the plan and print the code. And that's what we're doing here. So we, the library we provide has this compile method that compiles the plan into Python code, into executable Python code. And that's what you're seeing here. So what do? We, you see two loops here. There are three actually. Yeah? So the first loop loads the hash table. Yeah, maybe it's worth writing that on the board again. Yeah, if you now look at the logical plan here, where's my plan? Here's the plan. Okay. So what do we have? Simple hash join. So I'm just writing it as a tree here. Scan, persons. Then I have a filter and scan on books. Filter, scan, and here's books. Okay. Filter, price smaller 10. It's a condition. Price smaller 10. And there's a join predicate. Okay. So let's look at the code again. This is the code being created by our library. So for all the tuples I find in persons. Yeah, so what we're doing now is we're running a loop here. like this. Yeah, a loop covering this aspect of the plan that is everything here, including the build phase of the simple hash join. So bulk loading the hash table, not probing, just bulk loading. Yeah? That's what you're seeing in this code here. So for all the tuples you find in the input, you make an entry in the hash table using this set default. If it's not there, you create a new entry. So the hash table keeps a mapping from the name attribute. So the name is the join key, obviously. Maybe I should write down the join predicate here. So name equals author. That's the join predicate. Name equals author. Name equals author. Okay. So name, the hash table is organized having the value of key, the value of the name attribute as a key, and it maps to all tuples that have the same name. That's why you have this list initialization here, and then you append to that list. That's the organization of the hash table I'm building here for this operator in the loop. Then, once I'm done with that, I open the books relation, the file that contains the tuples of the books relation, and I run a next loop, and the next loop does all of this. Yeah, that's the next pipeline. So for every tuple I find in that input file, I check whether the price is smaller 10. Yeah, so that is this filter operation, this one line of code. If that is the case, for all the tuples returned by looking up the hash table I built here, I produce a join tuple and send it to the output. That's what the code is doing. Yeah? And that's a standard way how to compile this code. So you wouldn't have to output Python here. I could, and technically, also output C++ or whatnot. Actually, our Python database system could be instructed, we haven't implemented that, to not output Python code, but to output C++ code, yeah, and compile it, or WebAssembly, whatnot. Then use Python to issue C++ code, which is way more efficient. Yeah, but that's the core idea. And then you can compile that. So there are different ways of doing that. You can, here we are writing it to a file. The slide set is so big here. We create an executable file from that. And then we compile the code to bytecode using this compile method here. And then we call it as a sub-process from Python. And that produces, and that runs the code I just created. Yeah? So at the same time, so I'm creating a program from my program, then I'm compiling it to bytecode, and then I'm executing that bytecode here from the Jupyter notebook. Right, and then we also do a measurement here in that notebook at some point. Where was that? Here, so we do a simple graph representation. Again, these numbers will look different if it were C++ or something like that. But here we are varying the size of the input data set. And you see that in the interpretation approach, the times go up. Yeah? The more data we have, the times go up, whereas the running time for the compilation approach is more or less constant. That may differ based on data set, based on the plan type. Yeah? But you see that for certain types of queries, interpretation is a better approach. For others, compilation is a better approach. In general, for bigger queries with more data, because compilation is a good idea because you have to amortize the investments for compiling the stuff in the first place. What I showed initially, this trade-off here, you pay this extra price for compilation, and for small queries, that's not going to pay off. For instance, CRUD, create, read, update, delete. So if you have a simple lookup in a hash table or any other index, looking up for a particular key, compilation is not going to help you, not that much. It's really just simple looking up of keys and stuff. You don't need this stuff, but for more like analytical queries, heavy queries, compilation, plays a role and then pays off doing that. Yeah, so much about that. Right. Yeah, I think we talked about memory requirements. Yeah, so in summary, for pipelines, the summary is we have this blocking behavior of certain operators. That's a principal problem. Yeah? No matter how you implement the sort only works if it has seen all the inputs, tuples. Otherwise, you can't make a decision what is the smallest or what's the next smallest element. You have to be careful with memory requirements. So when organizing such a pipeline or creating a pipeline, it's not only thinking about computations, but also thinking about, okay, how much memory am I going to consume? Yeah, if you sort a terabyte of data, it's not going to work. Yeah. And there are these two paradigms in organizing those pipelines, and that's pull versus push, or any mix of these paradigms. So this pull style, or in C or iterator style, was widely used in disk-oriented systems. And why was it used back then? Because all these operator calls you had, all these cascade of operations, didn't hurt that much. What hurt instead was I/O operations. Disks were slow, yeah? And the I/O you had to perform from a plan dominated everything else. CPU didn't really matter, as long as you didn't do squarish complexity computations and stuff like that. It didn't matter. But once people made the transition to main memory databases, this started to hurt a lot. Yeah? So the costs of a plan you had a considerable fraction of the total cost of a plan were all these calls down the tree. Yeah, all these operations, next, were killing your performance. And that's when people made the change to either pass around batches of tuples rather than a single tuple to do vectorization, or to go towards compilation and or push-based interfaces. That's basically how history happened there. In general, you should try to use batches, large chunks, aka vectorization of tuples, because that gives you the best trade-off. So this idea of just passing a single tuple with the next call, that really hurts. That's too expensive these days. Okay, so let's talk a bit more about query optimization for the 20 minutes we have left. And some of that was already covered in the undergrad lecture, so if you're unsure about that material, please take a look at the videos. They're available in English and German. So here I just want to highlight a couple of few aspects. It's a bit more sketchy. Just want to show you some algorithmic aspects that may happen there. So in general, there is this problem in query optimization that if you have multiple joins, you can think about what is a join order, how to execute those joins. And here's an example. So if you have 3 input relations, A, C, and B, you can either first join C and B, that happens here, and then the result with A, or you first join A and C and then the result with B. That's called join order. And database systems, or most database systems that have a cost-based optimizer, try to come up with a decent join order, that, where you hope that the execution costs are the smallest possible. Because this has an effect in terms of cost. Yeah? If you look at the numbers here, you see that just by looking at the number of intermediate tuples produced, assume a situation like that. Of course, the overall result is always the same. It's not only the same number of tuples, it's exactly the same tuples being produced by those plans. So we have 2 different options to compute the same result. And if I assume that all of these relations have the same number of tuples, 1,000, for the sake of simplicity, this means that this join here gets 1,000 tuples from the left, and 100,000 tuples from the right, assuming that this join here of C and B produces a 100,000 intermediate results. May happen. I just set the cardinalities like that. In contrast, in plan 2, it may be that this join only produces 100 tuples, and those 100 tuples go into this join, and then you have a 1,000 tuples from B that go into the join as well. Yeah, the numbers could look differently, but this is the kind of situation you want to reason about. So plan 1 has to process 1,000 plus 100,000 tuples. Yeah? This top-level join has to process that. That's exactly the sizes of the inputs to this yellow join operation, whereas in plan 2, the top-level join has to process 100 from the left and 1,000 from the right. Sure, it depends on the complexity of the algorithm you're using in the join, whether that's a big issue or not. But if you think along the lines of our simple hash join, for instance, well, this is 10 times, you have to build a hash table that's 10 times larger than that one. Yeah? And you have 100,000 probes, where those 1,000 probes, yeah, that probably makes this top-level join more expensive. Yeah, that's one thing that occurs in query optimization, or one issue you have to worry about. And we will look at an algorithm in a moment. The other is the effects of a scan access plan. So whenever you're in a situation like this, there's a scan, or there's some relation, and then there's a select operation. You can either scan the stuff, yeah, meaning that this entire thing here is resolved by scanning the entire relation, or you replace the entire thing here through an index access with the hope that the index access is cheaper than scanning the relation in the first place. Again, it may be that depending on which index you use, the index access plan is, this plan here, is slower than the scan plan. Sounds weird, but it may happen due to problems in the storage hierarchy, random access. And that's a difficult problem in database systems because, in particular for unclustered indexes, where the leaf entries of the index go crisscross to the storage, you may trigger a lot of random I/O. We talked about that when talking about B trees. And that may mean that such a plan may become more expensive than an actual scanning plan. Yeah, maybe we skip that because, okay, maybe that's, I think I scribbled down the graph at some point in this lecture as well. But the problem here is really to understand it's not so trivial to make a decision, okay, I have an index, so I use it, because in particular for unclustered indexes, you can end up in a graph like that. So if you depict the selectivity on the x-axis, so how many results are selected, yeah? So many results means the entire relation A, all tuples from A are selected, whereas no tuples are selected. Depending on how many tuples you select, yeah? So depending on your selection predicate, your filter predicate, you may end up with a cost graph like this. Yeah, so the scan always has constant costs. Doesn't matter. It's just the scan costs you're paying once and the filtering doesn't hurt. But all these random I/Os you trigger may lead to the fact that using the index may be more expensive, way more expensive than using the scan in the first place. And that's not only 10 or 20%. That can be a factor up to an order of magnitude, or even worse, more expensive than using the scan. And that's a real problem in database systems to avoid these situations. Yeah? So what you want to have here is really, depending on the selectivity, you use this area, yeah? You use this plan. Yeah? So up to here, you use the index, and then you use the scan. Yeah? That's what cost-based optimizers try to achieve. Yeah, so back to join order. So we somehow have to evaluate these different options now. So given the plan, we have different options of ordering the joins or executing these joins. The joins in this example are restricted to binary joins. So we have to come up with the order of the binary joins. And the overall idea is you enumerate the set of all plan alternatives estimate the costs of each plan, and pick the plan with the lowest estimated costs. Done. That sounds easy. It turns out it's not, because the search space is relatively large. So if you have a couple of joins, say on 5 relations, A, B, C, D, E, then the search space here for the structure of the tree is you only have one. So left deep here means you join the first 2 relations, then the result is joined with a third relation, then with the next, and so forth. That's why you end up with a left deep tree. So the structure of this tree I'm depicting here, there's only one possible structure, left deep. Yeah? One here, then with the next, and the next, and the next, and the next. Yeah? But if you look at other options for these trees, you could also join it like that. You could say, okay, I join A and B, and the result was C, and then D and E, and the result was what I did here on the left side before. That's another possible structure of that tree. And the number of these structures can be computed through the Catalan numbers. There's a visualization for that. So here, this is for 3 relations. Yeah, you have these 2 structures, first A and B, then the result was C. Here it's B and C, and the result was A. That is for 3 relations. For 4 relations, you already end up with that. For 5 relations, you end up with all of these options. And if I can skip over that, the number of these internal structures of the tree can be computed with the Catalan numbers. Right, and that's only one aspect of that. And the second aspect then is, okay, now we have, for instance, back to 3 relations, we only have these 2 trees, these 2 structures, these binary structures, but then we can still vary how we label these leaf nodes. Yeah? We don't have to label it in that order. If A, B, C are my relations, I don't have to label it like that. I could also assign A to the first leaf, C to the second, and B to the third leaf, and so forth. So I have this 3 factorial number of orders of these 3 relations. And the same happens here. So that means the total number of plants is the number of structures, the number of binary structures, binary tree structures, times the number of orderings of the relations here. Yeah, I think, let's skip over that one. I don't have a slide here. Oh, there's a slide missing. But basically, yeah, but it's already visible here. Yeah? Yeah, so this is a 3 factorial. Because I have 3 relations, the number of orders of n relations is n factorial. If it were 4, it would be 4 factorial, and so forth. So I only have 3 relations. So I have 6 different ways of labeling that. Yeah? Those are my 6 different options here. A, B, C, A, C, B, B, A, C, and so forth, and so forth. And the same here. Yes? So it's always number of inner trees times number of these labels I have. And you see that goes through the roof pretty quickly, the number of options I have here. So what do I do with that? So what optimizers do is they do some sort of dynamic programming, typically. Yeah? So given a SQL query like that, with a couple of joins, you can translate this query to a query graph or join graph. Also talked about that in the undergrad lecture. Basically, each node now becomes a relation, A, B, C, D. And whenever there's a join predicate defined between 2 relations, you write an edge. Yeah? So here I have a join condition between C and D somewhere. Join C on C or D here. That's my join condition on C and D. So this is this edge. Yeah? And like that, you can represent the query as a join graph or query graph. Here is a more detailed explanation where you see, here I wrote down the join conditions plus the filter conditions on the individual relations. Here for these thin edges signal that, yeah, there is no join predicate specified here. I don't have it. And that implicitly means that's a cross product. If you were to combine C and A, You can't do that through a standard join because no join predicate was specified. Then you can only combine these two relations through a cross product, which is very expensive, of course. So the core idea of these algorithms is to use dynamic programming. There are many, many algorithms. We recently published something using A-star style heuristic search. It's another way of doing that. But what I'm explaining here is dynamic programming. And as for all these dynamic programming algorithms, you try to break the problem into smaller problems, try to solve the smaller problems, and try to reduce the result, the optimal result from a smaller problem. Yeah, so the assumption is there's an optimal substructure. The problem can be divided into smaller parts that can be combined into a globally optimal solution. And that's the idea of a dynamic programming table. You keep optimal solutions for smaller problems to reuse to solve bigger problems. And there has to be this overlap. So solutions to the subproblems may be reused, otherwise it doesn't make sense. So here's an example for how to solve that. So you keep a dynamic programming table, and this is a size-based enumeration. There are many ways of doing this. This is size-based, meaning I first look at subproblems of size 1. Size 1 meaning only one of the relations is considered. Yeah, so one of the relations, here this is basically a bit list saying, okay, here I try to find what is the optimal plan just to access the tuples from A. Yeah, how do I solve this stuff here? And then I list the options here. So there's a scan of A, or an index seek on A, on ISM access on A. These plans can then be fed into a cost model. So let's hope for, I have a cost model that tells me for each of these 3 possible plans to read tuples from A, what is the cheapest under my given cost model. Yeah? I do that for each and every input relation. I do it for B, those are the options, for C and for D. And then I prune. Yeah? So now I listed all the options, but then given my cost model, I identify, okay, that is actually the cheapest plan. This is the cheapest plan, this is the cheapest plan, this is the cheapest plan for accessing those elements, so I can discard all the other plans. I throw them away because I know they're more expensive than these other plans I identified. So I'm in this situation. So this is this substructure. You're seeing, okay, for this subproblem of size 1, that is the optimal plan. Once you're there, you start looking at subgraphs or subproblems of size 2. Seeing it here. So you get all these combinations. N choose K gives you that number. N choose, so 4 choose 2 basically. Here, this is 2, 2, 2, 2, 2, all these options. And for all of them, you list the possible plans to compute that. Here you see, okay, to join A and B, to combine A and B, oh, there's a join condition, so you can initialize a simple hash join. Maybe a merge join, maybe a co-partition join, whatnot, whatnot. You list all the options that are available. However, based on the subproblems you identified here already. So you're not reinventing the wheel. You know that for the individual access to a relation, I already computed the stuff here in the first round. Now it's how do I combine this stuff? How do I build bigger elements of these smaller plans? And you can list all of that here. List of that, list of this, of that. Here you see cross product, meaning there's no join condition. There's no join condition between B and C. Yeah, we have this thin edge. So the only way to compute that is a cross product. That's why I write cross product here. Again, I prune. I do that here. And what I'm assuming here as well is that I'm not exploiting the graph structure. So when you look at literature, you see that in this situation, some algorithms say, well, it's a cross product. It must go wrong, so I'm excluding all cross products. So some optimizers would immediately discard such a plan. Yeah, everything that has a cross product. However, that works in 95% of the cases, but not in 100% of the cases. It's already a heuristic. But that's a different dimension of the discussion. Maybe go there. We don't have time to go there. But again, back to the algorithm. So once you identified those plans, now you go into plans of size 3. Yeah, that's what you see here. Yeah, all those options, again, using plans of size 2 and 1. 2 plus 1 is 3, and 1 plus 2 is 3. Yeah, so that's how you can combine those plans, and you end up with those plans. Yeah, and then, yeah, you based on that, you can now combine these 3 with an axis on A, and these with an axis on B, and so forth, and then again cost that and come up with a plan of size 4 that's basically solving your initial query execution plan. And that's how you use dynamic programming here. And yeah, there are different twists to that. One is interesting orders. So interesting orders meaning the plan, you could have plans that generate the data in a specific order, as with ISIM or a merge join. And you can also tweak your dynamic programming table to do that. So if you have interesting orders, you keep plans for all the interesting orders. You see it here. So it's not only on the, you don't only look at the total cost, but here you keep 2 plans. This one doesn't create the results in a sort order, but this ISIM axis creates it in a sort order. So you just change the algorithm to not keep one possible optimal plan for the subproblem, but you keep one optimal plan per interesting order. So one for the non-ordered tuples and one for the tuples ordered by ID. Yeah? If there was another order on another attribute, you would keep 3 plans, or 4, or 5, or 6. Yeah? And that's how you change the algorithm. And then you can have the effects in plans as exploited last time on the board, that if you have 2 merge joins and one sorts on one attribute, that could be exploited by the next. You want to catch this situation in dynamic programming, and for that you have to factor in interesting orders. Yeah, I think in the interest of time, we have to cut it here. So there are many, many extensions to that, but bottom line is dynamic programming, and then that comes in 2 flavors. Either you consider cross products, or you discard them. I would recommend to consider them up to, I don't know, up to 10, 12 relations. You can enumerate them. That's one thing. And only afterwards, maybe you get rid of cross products. And the other option is you could factor in interesting orders. So if you have merge joins or any operation that produces an interesting order, like a sort order, you should enumerate that in dynamic programming. Okay. I was a bit quick today, right? Sorry. You can watch the YouTube video and slow it down again. Yeah, but that's all I wanted to show to you. If you're interested, we also have a notebook on that with some state-of-the-art algorithms, but we don't have time to go in the lecture into that. But if you want, you can take a look. That's it for today. See you on Wednesday.